For part 2 of our discussion on displaying data, we're going to look at some types of representations of data that allow us to compare two quantities with each other. So we'll be looking at line graphs and scatter plots and trend lines. If you'll notice, the word line appears in two of these three representations. And as it turns out, with scatter plots, we're also going to be looking at lines. So we'll have a little bit of a review of how to write the equation of a line as well. A line graph is used to show change in a variable over time. This is an example of a line graph showing the change in gas prices, and it's pretty clear from the line graph that you can see when the gas prices go up and when the gas prices go down. Here's another line graph. This one is from Missouri's Department of Elementary and Secondary Education. It shows the percent of students who scored at or above proficiency on the mathematics portion of the MAP test or their end of course exams for 6 years running. And here's one more line graph. This one shows the temperature in Celsius for each of 12 months of a year in Jamaica. So let's take a look at this graph and see if we can answer some questions about it. The first question is, which month had the lowest average high temperature? Well, the lowest average high temperature happened in February. You can see that was about 29 degrees Celsius. What's the difference in average high temperature between August and April? So we need to find the average high temperature in August, which is 33 degrees, and the average high temperature in April, which is 31 degrees, and we want the difference of those two, which would be 2 degrees. How many months have average high temperatures less than 32 degrees? Well, less than 32 degrees would have to be 31 degrees or lower on this graph. So that happens for 6 months. That would be in January, February, March, April, November, and December. Another way we can represent data in which we're comparing two quantities is with a scatter plot. When we draw a scatter plot, sometimes we'll see a pattern in the comparison of the two variables. If you look at the scatter plot on the left, you'll notice that from left to right, the dots seem to be going uphill. The data values seem to be increasing on both axes at the same time. We would call that a positive association. If you look at the scatter plot in the center, you'll notice that from left to right, the data values seem to be decreasing. That would be a negative association because as one data value increases, the other decreases. And the third scatter plot truly looks like a lot of scattered points, and it is. There's really no particular relationship between the data values. So in this case, we'd have a scatter plot with no association between the variables. Let's look at something that has a lot of data associated with it, and that's baseball. This is the top 11 batters for the St. Louis Cardinals in the 2013 season. There's a lot of numbers here, so we're going to concentrate on these two sets of numbers, the number of at-bats and the number of hits. And we're going to make a scatter plot of this information. So to make a scatter plot, we need to identify one of those variables as representing its values on the horizontal axis, so we'll say that that's at-bats, and the other is represented on the vertical axis, that's hits, and we look at these associated values as if we have coordinates, x and y coordinates of an ordered pair. So if we graph all of those ordered pairs, we do seem to have points that are falling in a pattern. In fact, they seem to have a positive association. It looks like the points are from left to right going uphill. So what does that mean in the context of this problem? Well, it means that as the number of at-bats increases, the number of hits also increase. Now let's do a little bit of an algebra review about how to write the equation of a line if we know 2 points on that line. And we'll use this as an example. Suppose we want to find the equation of the line through the points 1, 3, and 4, 5. So here's a picture of what's going on. We have 2 points. Point A is at 1, 3. Point B is at 4, 5. And we want to find the equation of the line. You might remember that there is a form of the equation of the line called slope-intercept. That would be that y equals mx plus b form. And if we can find the slope of the line, we'll be halfway to writing the equation. Well, slope is a number that represents the change in the y-coordinates of our points divided by the change in the x-coordinates. So sometimes we think of that as rise over run. It's the vertical change divided by the horizontal change. So we can see that the y-coordinates in the points have a difference of 2, and the x-coordinates have a difference of 3, so the slope of this line is 2/3. That means that from any point on the line, if we go up 2 and then to the right 3, we'll find another point on the line. Now if we're going to write this equation in slope-intercept form, we also need to know the y-intercept of the line. There are a number of ways to do that. Let's try this way though. We'd like to write the equation of this line in slope-intercept form, and we already know that the slope is 2/3. So the only thing we have left to find is the value of b, that's the y-intercept. Now you'll notice there's also an x and a y in that equation. That represents 2 numbers that are related to each other, and we can use these relationships we already know in order to find the value for b. So for example, we've got these 2 points, 1, 3, and 4, 5. Those are relations between an x-coordinate and a y-coordinate. So what if we pick one of those points out, like the 1, 3, which is saying when x is 1, y is 3, and we'll substitute 1 and 3 in the equation for x and y. And if we simplify, we'll find that b is 2 and 1/3. That's our y-intercept, which means since we already know the slope of the line, we can write the equation of this line, which is y equals 2/3 x plus 2 and 1/3. Let's look at another example of a linear equation. This one is an equation that describes the relationship between a Celsius temperature and a Fahrenheit temperature. How can we use that equation to find the Fahrenheit temperature when it's 10 degrees Celsius? Well, we're trying to find a coordinate, a value for F that corresponds to a value for C of 10. So we can substitute the 10 in the equation for the C and solve for the F. And we'll find that the Fahrenheit temperature is 50 degrees when it's 10 degrees Celsius. If you look at the graph, you can see that relationship as well. When it's 10 degrees Celsius, it's 50 degrees Fahrenheit. What if the information we know is the Fahrenheit temperature? We know that it's 68 degrees Fahrenheit, and we want to know the Celsius temperature. Well, we can use this equation to find the Celsius temperature if we know the Fahrenheit temperature by substituting that 68 in for the Fahrenheit degrees. If we simplify, we'll find that the Celsius temperature is 20, and that's also something you can see on the graph. When it's 68 degrees Fahrenheit, it's 20 degrees Celsius. Let's look at one more thing about this equation. We know that the slope of the line is 9/5. That's because the equation is in slope-intercept form. What does this slope mean in the context of the equation? So in the context of the equation means that the two things that are being related here are Fahrenheit temperature and Celsius temperature. What does 9/5 have to do with that? Well, if you keep in mind that slope is a change in y over the change in x, it's a rise over a run. And you think about what the variables are representing here. Instead of saying y, we're calling that Fahrenheit, and instead of saying x, we're calling that Celsius. So what we're really looking at here isn't a change in y over a change in x, it's a change in Fahrenheit divided by a change in Celsius. So what that really means, a slope of 9/5 is that when the Fahrenheit temperature changes by 9 degrees, then the Celsius temperature will change by 5 degrees. Now that we've looked a little bit at lines, we can talk about something called a trend line. A trend line is used to fit a set of data. In other words, we have a set of data that might be scattered, like a scatter plot is, but we want to be able to describe a line that is a fairly close fit for all of the points that we see represented in our scatter plot. So the way we draw a trend line is we just basically draw a line that kind of sort of follows the general direction of all of our data points. So we've got some data points above, some data points below, but generally speaking the line goes in pretty much the same direction as those points. If we want to write an equation of that line, we're going to need to know 2 points on the line. So we may need to adjust that trend line just a little bit to make sure that we've got a trend line that contains 2 known points. So this would be an example of a fairly good trend line. It's maybe not quite as good as the first one we drew, but it definitely goes through 2 points. And all we have to do is look at our table of values and see if we can figure out which 2 points our trend line is going through. That left point that we're going through is the point 328.78, and the right point is the point 554.164. So if we're going to write an equation of this trend line, we need to write the equation of the trend line through those points, 328.78 and 554.164. Now those are kind of awkward numbers to use. So we're going to make one more slight adjustment to make this a little bit easier. We're going to do some rounding here of the values to make these a little bit easier to work with. So we're going to round these to 330.80 and 550.160. Those aren't points that were included as part of our data set, but they're really, really close to points that were included. And since those 2 points will give us a trend line that is a good way to describe the data, we can certainly write an equation using these friendlier numbers. So we need to find the equation of the trend line through 330.80 and 560.160. So if we find the slope of the line, we need the difference of the y-coordinates divided by the difference of the x-coordinates. We've got the slope of this line as 4/11. The y-intercept of the line we can find by substituting that 4/11 into the slope-intercept form of the equation of the line for the slope, and then we simply need to find a point that's on the line to use as an x and a y that are related to each other. So let's go ahead and use the 330.80. 330 is our x value, 80 is our y value. And what we find is that the value for b, our y-intercept, is -40. So that's all we need to use to find the equation of the line, the equation of our trend line, which is y equals 4/11 x minus 40. What does that equation really mean? What does the slope of the equation mean in the context of this data? Well, the slope is 4/11, and this data is describing 2 things, hits and at-bats. So the 4/11 is telling us how the hits change compared to how the number of at-bats change. So that means that we would expect a player to get 4 hits for every 11 at-bats. So with that information, if a player has 121 at-bats, how many hits would you expect him to have? Well, we know in our equation the at-bats are being represented by the variable x. You can double check that by looking at the graph. So we know that the value of x is 121, since that's how many at-bats we have. If we substitute 121 for x, we'll find that y is 4. So if a player has 121 at-bats, we would expect him to have 4 hits. That seems a little off, doesn't it? And keep in mind that the reason that it's a little bit off is that we're looking at a trend line here. It's not exactly a reasonable thing to say that they're going to get 4 hits in their first 121 at-bats, but that's what our trend line is indicating. So that's a quick look at 3 types of graphs that we can draw. You may want to take a little bit of time to review writing those equations of the lines and interpreting those. That may be the most challenging part of this particular lesson.